wrong thing. Hi, everybody. So this is, again, section 11 to exponential functions. This is going over the homework. We just went over question 7. The answer is 4 teams, just multiplying by 1/2 each time. Okay, well, let's talk about 8 through 13. Find the next 3 terms in the geometric sequence. I'm going to pull some names here. That third period, here, second period. For the next 3 terms in that one, Travis, what did you have for number 8?
I had it was going up by -5. I did not see the direction.
Oh, you're right that it is going up by -5. So you got a calculator right there?
Yes, I did.
Why don't you do 250 times -5? I'll write in the answers here so we can all see it. So do 250 times -5.
-1,280.
Multiply by -5.
6,250.
And then do it again.
-31,250.
Very good. Okay, the next one, number 9. Baker, what'd you get?
I got 162, 243, 364.5.
Good, yeah, 162, 243, 364.5. Number 10, Ben, what'd you get?
I got 256.
Good.
204.8.
Good.
163.84.
Good. Yep. Now, do you notice here for each one of those here, I'm sorry, for 10, I'm going down, right? Remember, what do you notice about the R values for the ones that go down? They're decimal, right? The ones that decrease have an R value that's going to be a decimal. The ones that increase have an R value that's going to be a number bigger than 1. Number 11 here. Carson. I realize that. Well, get your calculator out and try to figure this one out then. Don't just sit there with nothing else. Why don't you get a notebook out too? That might be a good idea as well. We'll wait. Okay, what's the common multiple? 6 times what is 42? 7. So continue the pattern.
2,058.
Good. And what?
14,406.
Then what?
And 100,842.
Good. All right, let's take a look at the next one. Now, do you see how the next one alternates signs? What does the alternating sign tell us about the R value? Negative. Kyler, what'd you get for this one? Good. Okay, now this one's weird. I'll do number 13. I hope we didn't say divide by 4, because I would have to take off points for that. I agree, that is a pattern. But for a true geometric sequence, you have to think about what am I multiplying by? Yeah.
Times 0.4.
I'm times by what?
0.4.
It's not 0.4. If I'm dividing by 4, oops, 1 divided by 4. It's not 0.4, it's 0.25. So I'm multiplying by 0.25 each time. Now, I'm going to take 5/8 and multiply it by 0.25. And then I'm going to multiply, and then I'll put that into a fraction. So that's 5/32. And then I'm going to multiply that by 0.25 and put it in a fraction. 5/128. And then multiply that by 0.25 and put that in a fraction. 5/512. Now, what do you notice about the denominators? The denominators are multiplying by 4. Take a look at the denominator starting with 5/2. The numerator is staying the same. The denominator goes from 2 to 8 to 32 to 128. That's all multiplying by 4 each time. Take a look at number 14 here. The first term of a geometric sequence is 18. So a sub 1 is 18. And the common ratio, R, is 3.5. Find the 5th term in the sequence. So that means n is 5. So we say a sub 1 times R to the what power? 4th power. All right, let's do that. 18 times 3.5 to the 4th. And that gets me 2,701.1. 2,701.1. Let's see. Make sure I'm not screwing up any. Yep. Questions about that one? Let's take a look at the next word problem that we got. This number 16 here. Ball is dropped from a height of 500 meters. The table shows the height of each bounce, and the heights form a geometric sequence. How high does the ball bounce on the 8th bounce? So my A sub 1 is 400. My N that I'm looking for is 8. So I know I'm going to have 400 times whatever my R value is to the 7th power. I just have to figure out what my R value is. Well, to do so, I'm going to see what I have to multiply to go from 400 to 320. So the best way to do that is say 400 times what is 320? Well, that's 320 divided by 400. So my R value is 0.8. So that's the equation that I'm going to use. 400 times 0.8 raised to the 7th power. And that's going to get me 83.88. So let's say 83.9 meters. Questions there? Okay, let's continue on. Here's 17, 18, 19. For number 17, these are questions that the end of course test loves to do. Ones where it'll take out pieces of the sequence and make you figure out what pieces are missing. So take a look here. Alex, what would you say is missing out of 17?
I don't really understand the sound here.
Oh, that's right. Okay, so what do we do to go from 20 to 40 in terms of the geometric sequence? What do I multiply by here? Times 2. So keep that pattern going. What's the next two terms? And then? Exactly. Does that make sense?
Yeah.
So geometric sequence is just always repeated multiplication. All right, now, Liam, what would be my first term in that sequence? 2. How do you know that?
Because it's 2 less than 3. Or,
Well, what am I multiplying by to go from 6 to 18?
3.
Times 3, right?
6 divided by 3.
There you go. That's what I like to hear. Okay. So it's dividing by 3, right?
Yeah.
So what's my last term then? 54. Good. 54. And Serenity. For number 19, what would you say for that last blank there? I would accept the decimal here. What did you say for the decimal? It's not 0.5 though. What am I doing each time here? Not subtracting. Remember, it's continually multiplying. 1/3, right? I would be dividing by 3. So I'm multiplying by 1/3. So if I'm multiplying by 1/3, well, I would take 1 times 1/3. So what would be this line? 1/3 or 0.3. 0.3 repeating would be fine. I'll write it as a fraction to keep it exact. Again, the end of course test loves to do questions like that where it'll pick out. It's not going to just ask you what the next 3 terms are. It's going to pick out, okay, can you identify the different pieces of the sequence as long as we pull them out and give you some sort of pattern to go by. All right, determine whether each sequence could be geometric. Will, number 26, is that geometric? I'm going to say yes as well. What's my R value?
That would be 5.
Good. R value is 5. So it's yes, it's geometric. R value is 5. Berkeley, what did you say for number 27?
I said that it's not geometric
Why?
because it was going by uneven rates.
Okay, so 15 to 5. What would I be doing there?
Times 23.
Multiplying by 1/3 times 1/3, right? Is that the same case? Okay, 5 times 1/3. That's 5/3. Did I get what I needed to?
Yeah.
Okay, 5/3 times 1/3. Did I get what I needed to?
Yeah.
Does that make sense?
Yeah.
So it is geometric and my R value is 1/3. Make sense? Okay, these first two are geometric. I don't know about the last one. Rosalie, what did you say for 28? Is that geometric? Well, how do I go from 6 to 18? What would be the multiple going from 6 to 18? 3. Is 18 times 3 24? No. It would be way bigger than that, right? It'd be 54. So this is not geometric. Let me ask you this. Everybody pay attention real quick. Is 28 arithmetic?
Yes.
Is 28 arithmetic? Hayden Ryder says no, and I agree with him.
I agree with you.
What do I go up by from 6 to 18? What do I add there? 12. Is 18 plus 12 the next value? No. So this is neither arithmetic nor geometric. Something completely different. It doesn't even have a name, actually. The only named sequences we have are arithmetic and geometric. Okay, what's the first 4 terms of this sequence? Well, what's the first term? What's the first term? 3. All right. Now, I could plug in a sub 2. But what is the R value given this equation? No. What's the R value? 2. The base of the exponent. So I'm continually multiplying by 2. You see that? I didn't need to run the numbers in the equation. Could I have? Sure. I could have said, okay, plug in 2, plug in 3, plug in 4 to find the first 4 terms. But I didn't need to because I could see out of the equation the R value was going to be 2. And if the R value is 2, that means I'm multiplying by 2 each time. All right, let's get to our section 11.2 notes. The introduction to geometric sequence, exponential function. Today we'll talk about general form of exponential functions. On Monday, we will talk about exponential growth and decay. Do a lot of word problems. Today is more looking at the equations. Monday is looking at word problems. Yes, sir. Sure. I have no clue where that came from. All right. So exponential functions. Now, we've learned a lot about different types of functions this year. We learned about linear functions. We learned about quadratic functions. We talked a little bit about absolute value functions. And now we're going to talk about exponential functions. Now, exponential functions and geometric sequences go hand in hand. Exponential functions and geometric sequences are really essentially the same values. Let me show you here with an example. The table and graph show an insect population that increases over time. Take a look at the time and days. You see how the time, the x values are nice, evenly spaced x values. 0, 1, 2, 3, and so on. Look at the y values. Are the y values evenly spaced like a linear function would be? No, the y values are not evenly spaced. But what you can see within the y values is a geometric sequence. What am I continually multiplying by? 3. This is a times 3, times 3, times 3. And if you say that you have a continual multiplication, that is an exponential function. Just like arithmetic sequences were linear, geometric sequences are exponential functions, okay? The end of course test loves to do things where it says, okay, I'm going to give you a table of values, and you have to tell me what type of function it is. Usually it's either linear or exponential, or neither, or you don't know. Linear means constant change in x and a constant change in y. Basically, you could figure out what the slope would be. Exponential is, okay, do you see the common multiple? that constant ratio throughout, basically the geometric sequence within the y values. Take a look at what the graph looks like. Here's 0, 2. Here's 1, what was it, 1, 6. Here's 2, 18. Here's 3, 50. The graph of an exponential function is going to get really big really fast. I don't know if you guys had seen back, or you were paying attention back when the beginning of the pandemic started, the growth was exponential. And every time we go up into a surge, the beginning is always exponential. And then it decreases exponential as well. It almost looks like a bell shape, right? It goes up exponentially really fast and then down really fast. That's what happens with those types of things. A lot of things that occur in nature are exponential growth and exponential decay. One of the key numbers, and this is really interesting, my nerd brain, I was geeking out a little bit when we were starting this whole pandemic because they were talking a lot of math in a lot of those news conferences. You know what one of the key numbers that they were talking about? It was the R value. They kept talking about the R value. And they always wanted to say that the R value was either bigger or smaller than 1. Do you guys know what the R value they're referring to? The exact same thing that we talk about in our exponential growth and exponential decay. The exact same thing that we talk about in our geometric sequences. An R value bigger than 1 means the sequence is going to do what? Grow. An R value less than 1 is the sequence is going to decay. So that's why they were so focused on that R value. Bigger R value means numbers are going up. If the R value goes below 1, the numbers are going to go back down. That's one of the things that they were looking at each time. Okay, things like population growth, like bacteria population, or really population for any living thing, grows exponentially. Right. Every time something reproduces, it grows, and those things reproduce, and then those things reproduce, and then those things reproduce, and things grow exponentially rather than linearly. The function rule that describes the pattern above is 2 times 3 to the x. Do you notice what value did I start with in my table? 2. What value did I continually multiply by? 3. Do you notice how this is like the exact same thing as our geometric sequence? The only difference is instead of an x minus 1, I've got an x. That's really the only difference. And that's our general form of an exponential function. It's f of x, box it, circle it, do whatever you need to do. F of x is equal to a times b to the x, where a is our starting value and b is my constant ratio. A is your beginning value and b is your constant ratio. A is your beginning value, and B is your constant ratio. So you know what I can say? I could take any exponential function. I could take 4 times 2 to the x. What's my starting value of that function? What's my ratio? 2. So I know that this is actually going to cross the x-axis, or the y-axis, at 4, and it's going to grow by a factor of 2. It's my growth factor. I can say this. What's my starting value? 3. What's my growth factor? What's my R value? 1/2. Is this going to grow or get smaller? It's going to get smaller. It's going to decay, right? Because it's a number less than 1. It's going to go down. It actually ends up looking something, instead of growing, decaying like this. Will it ever go into the negatives? No. These will stay positive all the time. All right, let's take a look at an example. The function f of x is equal to 500 times 1.035 to the x models the amount of money in a certificate of deposit after x years. You guys know what a certificate of deposit is? It's one way to invest money. Right? It's called a CD, not like a compact disc, but it's called a CD, a certificate of deposit. Basically, what the bank is going to do is they're going to give you a good interest on your money just for putting the money in the bank. This is like a locked-in savings account. Like if you put your money in the bank as a savings account, you can take it out at any time, right? You can say, okay, I'm going to withdraw however much money. It's no big deal. It's just the money's just in the bank. A certificate of deposit is locked-in money that you can't touch for a certain amount of time. You can buy like a 9-month CD or a 12-month CD or a 3-year CD. Basically saying like, okay, I'm going to put this money in the bank and I'm guaranteeing I'm not going to touch it. So therefore I can get a little bit better interest on it, right? It's not going to, the interest in a savings account is not really good. The interest in a CD is a little bit better. You want to invest it in a stock, that's the interest rate is probably a little bit better. Or you want to put it in something different, the interest is going to be a little bit better. But a CD is a really kind of safe way to put money in the bank, but you can't touch it. If you touch it, if you try to withdraw on it, they're going to penalize you for it. They're going to take some of your money back. So this function says, okay, I've got 500 times 1.035 to the x. Think about that equation. 500 times 1.035 to the x. What's my starting value? So how much money do you think I put in the bank originally? $500. And they're saying, okay, in 6 years, this is a 6-year CD. In 6 years, oh, not 5,000, 500, excuse me. 500 times 1.035 to the 6th power. That's how much money is going to be there at the end of 6 years. 500 times 1.035 to the 6th. $614.63. $614.63. Now, you may be thinking, well, that didn't increase a lot. It doesn't in a CD. It doesn't. You know, it increased $115, which is pretty good, you know. But it sat in there for 6 years and you didn't touch it. But honestly, all that money is doing is sitting in the bank. That's all it's doing. You want more? You want a bigger increase? You got to invest it in a stock, which could go down or go up. You never know. Right? CD is very safe, but you can't touch it. Let's take a look at the next one here. I've got 200,000 times 0.98 to the x, where x is the time in years, models the population of a city. Let me ask you something. What's my starting value of the population? 200,000. What does the 0.98 tell me? Well,
Dropping slowly.
the population is decreasing. Decreasing pretty slowly, right? Because it's just under 1. 1 would be like the population staying the same. But it's just under 1. So the population's decreasing. It's not like everybody's dying off. But the population is just decreasing. People are just kind of like moving away, right? So if I want to know what the population will be in 7 years, I've got to take this formula times 0.98 to the 7th power. Let's see what's going to happen in 7 years. 200,000. Yep, 200,000 times 0.98 to the 7th. Okay, we got 17. Okay, I'm going to need to bring that over here. 173,625.11 people. Now, for our purposes, would I really talk about 0.11 people? No, but honestly, this is just an estimation, a prediction for the future. Whereas in that case, you can use decimals. I know there's not really 0.11 of a person, but when you expand, when you interpret data, it's okay to use decimals like that. Okay, when you're talking about things in the future. All right, so let's take a look at the back of the guided notes there. It says, remember that a linear function have a constant first difference, of a quadratic function has a constant second differences. Exponential functions do not have constant differences, but they have constant ratios. We talked about this at the beginning here. I said, okay, you got to see a constant change in x. Notice this. This is really important. Whoa. And this is where the end of course test can get a little tricky. They might give you something that doesn't have equally spaced x values. That might be a weird set of x values. But then the y values do something weird as well. Maybe you're not able to tell. You know what the best way I would tell you guys to do this is? Put it into Desmos in a table and look at the coordinates to see what type of shape it is. When you're given an exponential function, the shape should always be growing, right? It should always be growing. Let me show you what I mean when I say put it into Desmos. You could just open up pop open the Desmos tab, like when you're in your testing system, and then insert a table, Right? Insert a table. You could do this within the testing system. And then let me get my table here. 1, 6, 1, 2, 3, 4. Okay. Come on. And then 6, 18, 54, and 162. I don't know why I did a 5, but that's okay. But do you see my graph here? This is kind of hard to see that it is exponential. But is it getting really big, really fast? Yeah, that's a key indication of an exponential function. Something that's getting really big, really fast. So if you ever needed to, you could put it in a table to see what's going on, whether it be a linear shape or an exponential shape. Now, we should, if it's evenly spaced x values, be able to tell what that common ratio is. And more often than not, that's the way they give it to you. It'd be very tricky for them to not give you evenly spaced x values, but I've seen it before. Not very nice. As the x values increase by a constant number, the y values are multiplied by a constant amount. This amount is the a times b to the x. Let's take a look here. Tell whether each set of ordered pairs satisfies an exponential function. You know what I would do here? If this is written as ordered pairs, I'd rewrite it as a table. Go ahead and do that for yourselves. Rewrite it as a table. All right, do you see a common ratio? Do you see a common ratio? What is it? Times 3. I see a common ratio, and it's a common ratio of 3. You know, it didn't, so is this exponential? You would say, yes, this is exponential. And why? Because it's got a common ratio of 3. Now, it didn't ask for this, but we could write out this equation. What's my starting value? 0, comma what? 4 is my starting value. You always look for your 0, 0, comma 4. What's my R value? And that's my function. Y is equal to 4 times 3 to the x. Y is equal to 4 times 3 to the x. Go ahead and do the next one. Put it as a table. Is this exponential? No. What is it? It's linear. It's arithmetic, right? How do I see that this is actually arithmetic? Well, I'm adding each time. Oops, 64, not 46. Right? I'm adding 64 each time. That's how I know that this is linear. That's how I know that this is arithmetic. Okay? Adding each time means arithmetic or linear. Multiplying each time means geometric or exponential. To graph an exponential function, basically we're just going to choose values of x, positive, negative, and 0, and generate some ordered pairs and plot the points. So, you know how for linears we always just use -2, -1, 0, 1, 2? For exponentials, we increase that a little bit to see more of a pattern. We do -3 to +3. So, let's do it real quick. Let's take a look at this first one. So, I want to create myself a little table. -3, -2, -1, 0, 1, 2, 3. Now, we're not going to see any sort of symmetry like we did with quadratics. We're not going to see anything like that. But we're just going to generate ordered pairs. All right, we got 0.5 times 2 to the -3. We get 0.0625. 0.5 to the 2 times 2 to the negative 2, 0.125. So starting out really small, to the negative 1 power gets me 0.25. To the 0 power gets me 0.5. To the first power gets me 1. To the second power gets me 2. To the third power gets me 4. You guys see the common ratio within our table? I didn't even need to show it in the table because what you see that it is from the equation. What's my constant ratio within the equation? 2. Look at the base of the exponent, 2. Right? All right, now let's go ahead and graph it. Graph it on your graph there with me. Negative 3, comma 0.0625, so really close to them. And then negative 2, still pretty close. Negative 1, quarter of the way up. 0, halfway up. 1, 1, 2, 2, 3, 4. Do you see the exponential growth? You see how it's not a straight line? It's going to curve up and continue in that pattern. Will it cross below the x-axis? No. It will stay above the x-axis. It's just going to keep getting smaller and smaller and smaller. You know what's interesting to point out here? Everybody look up at the screen real quick. What's my starting value within the equation? 0.5. Where does it cross the y-axis? Those numbers are always going to be the same. The y-intercept is always going to be your a value, the one that's multiplied to out in front of that b to the x, that 2 to the x. Let's do one more. Negative 1/4 times 2 to the x. Negative 1/4 times 2 to the x. Okay, so again, negative 3, negative 2, negative 1, 0, 1, 2, 3. I know it seems like a lot, but that's our best way to graph it right now. Could you put it into Desmos? Of course. But if we wanted to copy that graph onto something or find specific points, we would need to just generate a table. All right, so let's do it. We got negative 1/4 times 2 to the negative 3. Negative 0.0325. You know, I'm just going to do a bunch here and copy them into the table in a second. Oops. To the negative 2, to the negative 1, to the 0, and I'm going to bring this over. And then we're going to do to the 1 power, to the second power, to the third power. Okay. There we go. All right, so we have negative 3, negative 0.03, negative 0.06, negative 0.125, or yeah, sure. Negative 0.25, negative 0.5, negative 1, negative 2. All right, now we graph it. We get these guys to go away now. So long. And we graph here, negative 3, pretty close to the axis still. Negative 2, pretty close to the axis still. Negative 1, pretty close to the axis still. About a quarter of the way up. About a half of the way up. Oh, shoot, I'm not going negatives. Whoops, these are negatives. They should be below the x-axis, the y-axis. Here we go. Sorry about that, folks. Thanks. 0, comma, quarter of the way up. 1, comma, halfway there. 2, comma, negative 1. 3, comma, negative 2. There we go. So those are general exponential functions. Could I still go in and use decimals if I wanted to? Like if this was on the test? Of course. Let me cancel out what's in there. I want to do negative 1/4 times 2 to the x. Negative 1/4 times 2 to the x times 2 shift 6 x. And let me zoom in a little bit. And do we see it just as we saw it on our table? Graph there? So you can use decimals along with it when you're in the test. Yeah. Yeah, you'll need some graph paper for your homework if you want to pick up some. Hey. So long, everybody. Playing along at home.